Hello, am I audible?
Yes,
Yes,
sir.
sir.
Okay,
Yes.
very good evening, everyone. So, welcome to the WeeK-4 that problem solving session. So, I hope you have watched the WeeK-4 lectures and you have joined some previous session and you have understand the algorithms of the WeeK-4. So, today we have some problems. Basically, depends on that WeeK-4 concepts. So, as you know, that WeeK-4 is basically that graph basic algorithms likely the traversal algorithms and some we have topological sort algorithms. So this is the basic graph algorithms. I hope you have understand that representation of the graph in our that programming language. So how you are representing or how you are storing the data in of the graph actually in the programming language, which data structure you are using, how we can represent the that graph data. Okay, and so the problem is also based on that. So let me share my screen and we'll share the problem. I have released the problems. So total we have three problems today uh, in the live coding. So let me share my screen. Then we will discuss. Okay, I hope my screen is visible.
Yes, sir. It is.
Okay, yeah. So regarding one thing, so today actually these three problems, live coding problems, actually these problems are taken from the initial terms OPP exam. Okay, so do not skip these problems. We know that at the last moment, most of the students ask for the PYQ questions for the OPP exam also, but generally that not released. So, but problems are already included. Many problems are already included in the content. And similar that weekly practice theory assignment also. Okay, so also do not skip that because we have included PYQ questions in the practice theory assignment as well. Okay, so if you open then this practice assignment 5 like this, so you can see these 5 questions. So that initial 5 questions are basically not the PYQ, but after that, the sixth, seventh, eighth, these questions are directly taken from the PYQ questions. Okay, if you have the PYQ sets, you can find out these questions in the any of one of the term. So we have included this for the practice. You can discuss these questions in your TA sessions or any that open session if you are finding difficulty to understand these type of questions. So you will find the similar type of questions in the exam also. Okay, so just do not skip these practice theory assignments also. Okay, so because maybe some similar question you will get in the final exam. Okay, any quiz exam. So similar to that OPP exam, so do not skip this live coding problems and try to solve because and this time we have also make this as a bonus activity. So you know that 3 marks is for these live coding problems actually you have, and 2 marks for the mock. Okay, so now we will discuss these three problems. Dhruv, yes, go ahead.
Sir, I want to ask that there is the difficulty level of week 4 is too much high, and we are facing some issues while studying this. Can you guide us? How can I improve the
Yes,
coding
sir.
and the level of
Difficulty.
yes, sir.
So, what difficulty you are facing? Just first tell me this.
Uh, the difficult. I am facing difficulty in understanding the concept and also applying it to the code. I have tried the practice questions, but I am not able to solve them.
Okay. So, first thing, all algorithms concepts are clear or not? Because I think this DFS algorithm, BFS, DFS, you have also learned in the previous course as well. I think CT and math. Am I correct?
Yes,
Yes,
sir.
sir.
But the main problem is that I'm
Implementation.
yeah,
Yes.
how to implement it in code.
Huh. So that is actually yeah, some definitely practice is required. You cannot write a code in a single time like single run. So just break the algorithms in steps, small steps. So what you are doing step by, just complete the each part and then check you have done correctly that part or not. Then move ahead. Okay. Do not try to write a direct code in one run. So in the initial things, the first thing what you can do after watching the lecture, just after understanding the steps, just try to apply the dry run on some examples, okay, of the algorithms. Okay, so what you can do in the graph algorithm, suppose you are using the BFS algorithm, if you are applying the BFS algorithm, so what you have actually understand by the algorithm concept or just in the lecture, just apply these concepts on some random graph. You can take any random graph and just apply each steps on paper and by the paper and pen, and see what happened actually, how algorithm is working. Okay, so how algorithm is working, how the steps are going, and how the nodes are traversing in the graph. Okay, so dry run is much required for this to understand the concept very clearly for these algorithms. Okay, so because of that, we have added this that PDS in notes. We have added the that visualizations also. Okay, so
Yes.
if you open this WeeK-4 notes, like any algorithms are like BFS, if we talk about, you can directly first see visualization. This is via some slides, but otherwise some visual algo tool is also there. So I think that is included at the end. Uh, let's see. Yeah, this one. Okay, so here there are many algorithms are there, so that DFS, BFS, this you can select the algorithm here, like BFS, and then you can run this algorithms and just try to understand that how it is working actually go. Okay, so how that nodes are actually checked, you can just look this how algorithm is working, or you can just slow the speed, this is slower one, or you can just pause in between, so how the steps are moving, how the nodes are actually traversing. This is the one way you can visualize this. After that, take any graph and just draw on the paper, and then by your pen actually just mark that how the algorithm is proceeding in the graph. Okay, then just try to write the implementation. That part is not clear, that dry run part, understanding of the working of actually algorithm is not clear, then you can also not write the implementation. And for more clarity regarding how to understand the algorithms, so we have actually added this steps, actually not the algorithms like pseudocode. Okay, we have added this steps in normal English language, what actually you are doing. Okay, so these steps are just a overview steps what actually we are trying to do in the algorithms. You can first read these steps. Okay, after reading this step, then you can see visualization of this. So this is through the slides we have created how the actually how data structures are filled at the each steps. Okay, so we are maintaining one queue, we are maintaining one visited dictionary, then each steps when we are selecting the node, what value are actually filling, and how the nodes are actually traversing. So we are selecting 0 nodes, then we will select the adjacent of 0 nodes. In that case, in this step, how the queue is actually updated, how the visited dictionary is updated. So just understand these steps, how the data structures are updating, okay, which we are using in the algorithm. So, and then after understanding this concept very clearly, then try to write the implementation. Okay, and also once you will understand these steps, after that, if you want to look the implementation, actually that will also be clear to you for understanding. Okay, so there are many ways we have actually added this. So first thing, you can just read these steps. After that, you can see some visualizations of the steps, and there are another way of the visualization that by the visual algo tools, and then you can apply the dry run by some random example. Okay, and then just see the implementation. Then you will find out that how that implementation is working. Okay, so this is the flow to actually learn this course, not directly. If you are looking, suppose if you know that algorithm concepts are not clear, you have not applied that algorithm on any graph by your pen, so definitely if you're directly looking this code, you will get stuck at some points, how what happened, how we are taking this data set, why we are taking this data set. There are many questions will arise.
Sir, one thing I also want to ask that
Mhm.
how much time should we give to a particular question? For say, let's we are solving the question of the live coding session. then
Hmm.
how much time should I
No,
pay for?
initially don't think about this time. Actually, these assignments are open actually. Okay, so because for this course you have to, maybe in initial time, maybe you will get maybe 1 day to solve one question. Okay, but maybe after understand, after getting this, after doing this type of practice 1 month or 2 months, maybe your that you will get more efficient to write a code. You will get less time after that. Okay, so this actually improves the that your coding skills, but it takes time. This is
Wow,
not like a you will directly write a code, solution code in the first day, in the half an hour, like this.
thank you.
Okay, so just do the practice, give the time. Do not just skip the problems. If you are facing difficulty, just take some break and just think about that in the break. What problem you are facing? What are the solution for that? And then again try. Okay, after the after sometimes maybe after solving 40 50 problems, you will get that now the new problems are coming, just a overlap of that problems which you have already solved, like superset of problem. You have already solved the subset, but now you will solve a superset. So some part of that problems you have already done before. So you will get a less time to solve again that part. Okay.
For the OPP, sir.
OPP, no, I am just saying that now OPP have maybe, so OPP will be conduct after 2 months approx. Okay, so I think in the December month. So you have this October and then November. Just try to solve all the problems which we are providing, and our TA is also providing some basic problems from the lead code, and also try to solve by your own some easy level problems first from the competitive uh, platforms if you have the time. Otherwise, that our course problem is also enough for the practice. Okay, so yeah, some problems, yeah, definitely we are that some problems are actually in the course are difficult. That's are actually challenging problems, like WeeK-4. If I talk about this in practice problems, so, that problems we have added in the practice or some uh, these assignments. So like this, where is the PPA? No, these are the live coding actually. Okay, so like this PPA 3. Okay, this problem actually is not a very easy problem. This is challenging problem. This is the competitive problems. Some problems we have added. Okay, and so we expect that those who are actually very efficient, this problem is actually for them. If you are this is the competitive problem. Just if you are facing difficulty to understand the problems first. If you are not able to understand what is this problem, just discuss this problem with the TA or in any live sessions. Okay, those who feel that they are actually very efficient in the competitive platform, those who have the prior experience, they can try. But we are not giving this type of many problems. Some problems are actually added, but not all. Okay, yeah, so many hands raised actually. Yeah, next is Joy Dev.
Yes, sir. Sir,
Yes.
so today I was solving some problems, so but I couldn't solve a single problem.
Mhm.
Uh,
From which
Maybe
week?
you can week two, GRPA 2. Yeah. Okay,
Uh-huh.
so I have tried and I have understood the things, but when I have tried it, so it is giving different type of answer. I have done dry run in Google Colab, but it is not. Have you seen this question?
Let me open.
Uh,
Week 2, which problem? GRPA?
Two. Uh,
Find largest.
yeah.
Okay.
So sir, suppose if I take sometimes in 7, 8, 2, 4, 5. Okay. Uh,
Hmm.
if I take something different, like if I take a 7, 8, 100, 2, 4, 5, then
Hmm.
it is sometimes giving largest number is 2, sometimes given 4, sometimes given 100. Uh, this type of things is happening.
So in this question, what is given actually? So find largest, and it is also saying that find the solution of log n time. Okay. If the problem is asking regarding like this log n time, these things where you can just think about it, divide and conquer approach. That is actually binary search. Here we are searching something. Okay, we are searching the largest element, and some list is given, and we are assuming that n elements are there in the list, and we need a solution of log n time. So how that can be achieved? Only if you can divide the problems into half at each steps. Okay, then you can achieve the solution in log n time. After that, now you can think how. So binary search is the one way to searching the solution in log n time. So now directly by binary search we cannot apply, the standard binary search we cannot apply. But here some so this is mentioned there. This sorted list is actually rotated. Okay, this is rotated list. So after rotating, just take some example, small example. After rotating the list, just figure out that because still this list has some pattern. Okay, after rotating, you will feel that in the first look you will feel that elements are now not sorted, but still this list have some pattern, because this is just a sorted, not just a randomly flattered all the elements like this. So here you can just recognize that what pattern is there, how you can identify the largest element, what is the actual identification of the largest element in this pattern. Okay, so if you rotate this list, uh, you will see, if list is not rotated, definitely largest element will come at the last. Okay, so, and if list is rotated, so like take some example. So this here you can see, so in the sample input, if list is rotated some number of times, so definitely the all adjacent neighbors of the largest element will be the smaller element compared to this. So this is the identification of this greater element. Okay, so here now if you see the other element, you will see a pattern. So like if you check this 4, the left element is actually smaller, but right element is greater. So here this pattern we are not finding with this, but with 8 actually, now the left element is also smaller, right element is also smaller. Then this is just a one identification where we can find we can say that this is the largest element. You cannot see this pattern with any another elements. Okay, this pattern you will get only for the largest element after rotations. So just what you can do, you can directly check the middle element, similar to your binary search. Check this condition. If the both adjacents are smaller, return this element as a largest. Otherwise, now how you need to skip the part, actually half part, left part or right part, which part you need to proceed further. So that is also we can decide. Okay, so that we can figure out the pattern. So like in this pattern, if we are supposing check 2, okay, and 2, this left side element is greater, right side element is smaller. Okay, so if this type of pattern we are getting, so what we can decide that if left side element is greater of 2 and right side element is this smaller, or we can also decide based on the first element like this. Okay, so like yeah, we can decide here for some conditions. So based on that we can decide which part actually we can move here. So in this example, let's we are coming on the 2. So how we can decide? Yeah, so we can compare 7 and the last element. Okay, so 7 is greater than 5. So in this case, our bigger element will always become on the left side. So we can discard the right side in this case. If our middle element is not following that condition, both neighbors are smaller. So then we will check our corner elements. So 7 and 5. So 7 is greater than 5. That means our largest element is now shifted to this side after rotating. So we can skip the right part and we will check the same things again on the left part. So now the concepts are very same, similar to the binary search, but only the things are changed. Just a identification of the middle element, not middle, largest element, or just a way to remove the half part. that things are actually changed in this question. So just think about this, how you can, that identification I have already told you, that largest element, that is the identification. Otherwise, you can simply just figure out that how you can remove the half part, or how you can figure out the part which you need to check next in the same way. Okay, so I hope you get some idea for this, how you can proceed this question.
Yes, sir. Yes, sir.
Okay, so like this type of questions, just first thing, log n solution means binary search type of concept we need to require. After that, just figure out the pattern and just check the elements, what, how that element can be identified. So there are many type of questions can be asked on the binary search, like this is one a largest element in the rotated list. Some I think you have already seen one questions where the peak element in the pattern, where the first elements are increasing then decreasing. So then there is one type of questions. Another question is possible, like suppose if you have a list where the all elements are there from 1 2 3 4 continuously, but only one element is missing. Okay, you have the element of from 1 to n. Okay, but one element is missed, otherwise all elements are continuous in the continuous way and distinct. How you can, how we can identify that missing element? Okay, so then you can think about the binary search concept. Same things, if all elements are distinct, only one element is duplicate in the list, and our elements are in the sorted way. So how you can figure out that duplicate element in the log n time? You can think about the binary search in this type of questions. Okay, so some pattern definitely will be there. Okay, you will not get the similar type of problem simple binary search. Okay, so we will not ask like this, we are giving a sorted list and just apply the binary search. Okay, so this is exact similar things of the algorithm, but what are the other use case possible for that algorithm? So that we have to also think, what are the other possibility for the problem. So okay, so this type of problem, some pattern you have to figure out.
So to find duplicates, we have to sort it, right?
No, I'm saying that we have the same continuous sorted order, like 1 2 3 4 5 6 in this way, but in this sequence one element is only duplicate. Okay, so and we need to identify that number in the log n time. This problem can be solved in the n time, but we are focusing on the log n time solution for that. So then you can think about the that binary search concept for this also. Here we can take the help of indexing. Okay, so we can simply check the middle element and we can compare the index for that. If an index is because we know that the first element index will be 0 and last index will also be increased the similar way, and we can figure out the pattern. Same if our index is not mismatching, if our index is mismatching actually to the number, so that we can figure out that which side actually we need to check further. Okay, so same way, if you are learning any algorithm, just think about that, what type of problems can be actually framed for that problem. So you know that you have learned many sorting algorithms. So now sorting algorithm is purpose is same, the sorting the element. But now professor have discussing about the use case also regarding this DFS, BFS. So if you are learning BFS, so that means we are traversing something. Now just think about that, how that graph actually can be used in the real life scenario. Maybe some network, some road network, some like a airport network, or some that communication computer network. So in this way, that can be that we can imagine like that graph can be framed. After that, we can think about the problems. Okay, so same way we are traversing here. So if we are sending some that message, so how much time that will that it will take for the communication. So that we have actually included in your assignments. So all the problems are actually just a use case of that algorithms. Just you can internally actually you have to use your algorithms. Some story is actually added. So that is the same things actually asked in the competitive programming. So what they actually did, they know the algorithm. After that, on algorithm they design the scenario. They know the solution first, and after that they design uh, some story scenario on that problem. So same way you can also start thinking. If you understand the algorithm, then think what problems can we actually frame. What type of problem? And you know the solution that this is the algorithm. We are thinking the problems which can be made for these algorithms. Then you will also understand the applications or use case of the algorithms. Okay, so because of that, we are not asking the straightforward questions here. We are not asking like just write a implementation of BFS, write a implementation of DFS. We are giving some story in at the back end. Algorithms will be used. The same type of algorithm will be used to solve that problems. Okay. Yeah, so Bhumika.
Yes, sir. So I need to ask, like, how to solve PPA and GRPA, sir. I'm really facing difficulty in, like, solving questions. Could you please
PPA and
guide?
GRPA.
Yes, sir. So generally, like, I'm asking, up to week 2, it was fine, but from,
So first week was simply on Python. Nothing is the new things actually. Yeah, second week is the main TSA started. Okay. So okay, PPA definitely you can take help. You can take the help of if you are not understanding or not getting any hint for the solution like this. So definitely you can take the help. Okay, of the in the session you can discuss these problems in the TA sessions or in our session also. And also do not ask for the solution actually. Okay, just ask for the logic. Okay, after that try to write the code by own. So Python, what you have already done actually, Python you figure out the logics, you figure out the logic and then you try to solve the problems. But here if we are also giving the logic, some logic to you, but yeah, that logic have some standard algorithms or some big concept actually. But still after getting the logic, writing the solution, that skills should you develop actually. Okay, otherwise if you have the logic, suppose if you works in the company and they just get giving you the some logical idea that you need to implement all these things, this is the overview, like this is the logical things you need to do this thing. After that you have some capability that after understanding all the that steps or this algorithms, then implementation task definitely is your skills. Okay, so that Python in this course we are not teaching the Python, that what are the syntax things. After getting the logic, definitely you should try to implement that. So like selection sort, what is the selection? So you can write a implementation of selection sort.
yes, sir. Like, I,
So you now you understand the concept of selection sort. What we are doing simply in general in the normal steps. I'm not asking the code here. I say what we are doing every time we are selecting a smallest element and we are just shifting that element at the first position. After that, in the remaining elements, we are again finding a smallest element, then shifting to the second position. Same things we are repeating. Okay. Here, no need to remember any codes. Now, this is the simple concept of the selection sort. Just try to write code for that. Okay, so do not learn the solution, do not learn the code. If after getting the logic, definitely you should focus to implement. Yeah, coding is not a magic. Practice is required. Too much practice is required. Time is also required. Without giving the time, you cannot directly become a very good programmer like this. And it also takes the time. And sometimes, if you are facing, maybe in the first run you are facing the difficulty in the SA course. Um, so after maybe one run, maybe you will get some grade like some smallest, lowest grade like BEC or something. But when you will learn the same course again, you will find that this course is actually easy, not the tough. But this actually requires some time and practice. Okay, so give more time, just think more, and also use the paper and pen for this.
okay, sir.
And also do not too much focus on the previous that your senior comments or senior post like this is very difficult, this is very difficult. There are many posts actually students have posted, and many of the students actually are doing the TSAP also in this course. So you know that your TA is also done this course. Now he's actually expert in the each. He's now teaching everything. Okay, he's also actually not a like a that experienced person in the DSA course. He also learned first time this DSA course. After that, he give more time after the course done. Then he applied for the TSA. Now he's doing very well. He's also creating new problems. Okay, so just give more time. Do not uh, motivate yourself. Okay, so this is the only things you have to give. Actually, you have to give only. So we are conducting like 5 live session. I hope you know that we have added one more session on the Sunday. Okay, if you have any doubt, then you can also join the Sunday, and regarding the doubts only.
Sir, that session is from next Sunday, na?
For not for this Sunday, from the next Sunday.
Thank you, sir. So it will be really helpful, sir.
So that is only for the doubt session. So just first step is just watch the lectures and try to just collect all your doubts, okay, and ask all doubts in the live sessions. So total 5 live sessions are running for this course. You just clarify all the doubts. Okay, ask the logic or solution approach for the PPAs, GRPAs. GRPA you can also discuss. Some logic idea you can discuss, solution you cannot discuss before the deadline. Okay. Yes, one.
Okay, sir.
Okay, so let's come to the problems, today problems. So live coding that yeah, so this from WeeK-4 actually we know that the algorithms are increased because WeeK-4 there are many algorithms discussed in the lectures week 5. Because of that we actually reduce the content also. Now we have removed the one week completely from the course. So now this course is actually a 9-week course, because the first week is only Python. After that we have removed 1 week from the last. So you have the slave content till week 9. After that one more week is there, week actually 11. So week 2 to week 9 and then 11. Only 9-week content is there in this course. We have removed one last week actually in the course because of this heaviness. Okay, so let's come to the problems and we'll discuss the approach and we'll try to write solution also.
So small request, sir.
Yes, Sanjay.
Before going to the coding, please try to explain in brief about the logic or algorithm behind.
I always done this actually.
Okay. Because the open sessions are to be conducted at tomorrow or day after tomorrow. We are ahead of those sessions.
Okay. So I'll also discuss only the approach actually. Okay. So that is the main agenda of this. I also want to ignore the direct solution. I want to discuss the approach only, and I just also wanted to approach from your side. Okay, so if you have also another approach, you can also discuss. So as you know that any problems may have the different approach. So if you are getting some different idea in your mind, you can also discuss. So okay. So now the first problem is the shortest path problem, and here we are solving the problems like concept wise, okay, week wise. So we have also know that these problems are based on some WeeK-4 concepts only. We don't need to think about the outside of this. So just think about that. If you're reading the problem statement, just figure out that what are the internal things actually it is asking, which algorithms is relevant. Okay, so regarding the shortest path, this is the first problem of today. The story, this basically is the express train routes are provided in the adjacency list, A list. This is the name. Now the adjacency list. Okay, this should also be very clear. And now this adjacency list and adjacency matrix are two ways to represent the graph. Adjacency list we are implementing using the dictionary, Python dictionary. Adjacency matrix we are representing using the nested list or maybe 2D array using the numpy. Okay, so this implementation, that means representation, should be very clear. Here you have to find the root from start to end with minimum number of possible. Okay, uh, what is possible? Here you have to find the root from start to end with minimum number of possible. I think something I missed. Okay, possible hopes. I think. Okay, that steps is missed. Let me open this new run. Okay, so this is actually with minimum number of possible that hopes. Write a function minimum hopes, that is the function required for this, where the data structure is given as a list, start node is given, end node is given. To return the city to be visited starting from start to end, return a list with only start if the end is not reachable. So here we need to find out a root. Okay, here start and end point is given, data structure is given, and it is asking for, we need to find out a path. Okay, so that means what is the first node is start, after that what will be the second node in the path, then what will be the third node in the path, and this path should be the shortest path in the terms of minimum number of nodes in the path. Now my question is this: if we are looking for the shortest path, okay, this shortest path is not the weight something, okay, in the edge, like because this is not a weighted graph. Here we have simply a linked edge between the nodes, and shortest path means here is we are looking only to a path which have the minimum number of nodes in the path. So can anyone tell me which algorithms we can use to find out a shortest path?
Breadth first search.
BFS.
BFS. Okay, now why BFS?
It will search
Because it checks level by level.
Level by level. Okay, or we can say adjacent by adjacent nodes. Okay, so yes, correct. So this BFS algorithms always check the nodes which are directly connected to them. Okay, that it traverses all the node first. That it will complete all adjacent node first, then it will move to the next adjacent level. So our elements are traversed in this way, adjacent by adjacent, like this. So we will always get a shortest connectivity. So like this, I'm just making in the different form, so that is called as a tree things. So 1 second, I'm getting some notification. Okay, so suppose this is a starting node, and after that we have some adjacent like 3. Okay, so this 3 first we will traverse all these 3 nodes, and after that we will check the next adjacent level of this. Okay, so that means suppose this is the A node and this is B and C and D. So after we have traversed all these, so what is the distance in between these? This is the starting node and this is the next level. So the distance is just simply a one edge in between. Okay, after
Yes.
that we will check a next adjacent level. So that means what are the adjacent of B? So maybe some more, suppose E and F are connected from this. Okay, now if any node is visited, definitely we will not visit again. So we will check the adjacent of C. So like if G is there, and we will check the adjacent of D. Suppose H is there. Okay, so now the distance for this or this level is actually 2, which is actually a minimum. Okay, so this distance is actually a minimum because we are traversing the node adjacent by adjacents, and only 2 edges there in between. Okay, so we are getting a shortest path in this type of traversal. Okay, so this is creating a like a traversal tree. So in tree, from root to leaf node. Okay, so this is called as a leaf node, which doesn't have the further child. Okay, further connected nodes. So from this node to this leaf node, we have the only one path, and this path is actually a smallest path, the shortest path. We can say that. So that means BFS traversal actually we can use to find out a shortest path. 1 second, give me 1 minute. Okay, so here now we know that the purpose of the BFS algorithm is actually to find a shortest path. We can figure out that, and after that we can also find out the connectivity. You know that this traversal algorithm is basically just traversing a nodes in the graph, and by this algorithm we can also check the connectivity in the graph. Okay, so if we are starting from A, what are the nodes we can reach from this A? Okay, that are actually connected. So that connectivity we can check. We can connected component. So connected component means suppose this is the one part of the graph, this is the second part of the graph. So this is called as a one connected component, this is the another connected component, okay, of the graph. And these two components are not connected. Okay, so that things we can also identify it by the BFS algorithm, because BFS algorithms also provide the reachability, that it is reachable or not. So that things we can identify that. So now you can, you know, the basic purpose of this algorithm. Now you can also figure out that what problems can be asked from this. Okay, so like some network is given, road network is given, and we are asking that any city is reachable from that city or not. So now the same graph, some story word actually added. Okay, so connectivity can be asked like this. Okay, shortest path can be asked in the terms of number of city in between. So like this things can be framed. So in this question now, what is it is asking, that it is asking the path actually. Okay, so here start end is given, the data structure is given where the all data is there of the graph. You can see the graph data also. This is the view of the graph data that is in the form of dictionary. So each that this, you can see this zero is basically a that the source node, and we can we have directly connection between 0 to 8. Okay, so like 0 is this one and 8 is this one. Okay, so 0 is 8 connected. Okay, now from 8, so 0 is connected and one new node 9 is connected. So this is the connectivity, we can understand that. So for this type of question, you have the data in this form, but at the time of problem solving, you're in the mind, this should be come in the picture. Okay, your working should be, your imagination should be on this actually logical graph, but data you have in this form. Just when you are working on the data structure, so your in your mind this graph should be come when you are just dealing with this type of graph. Yeah, Doril. Yeah, sorry, what's your name?
Please repeat, sir. We couldn't get it.
So this is actually a adjacency list for the graph. Here each key of the dictionary is represented the source node or vertex, source vertex, and the elements in the list, corresponding value list, it's actually are directed connected nodes. Okay, so that connected nodes, so 0 to 8. So 0 is the source, 0 to 8 we can read like this. Okay, 0 to 8 we have one edge. Okay, next line 8. 8 to 0 we have one edge. So this is actually undirected graph, so we can read like this, 0 to 8 and 8 to 0 both sides. 8 to 9 we have some edge. So okay, 8 to 9 we have the connectivity. So this is just representing a connectivity of the graph. So 1 to 3, so like 1 to 3 is connected. Okay, so 1 to 5 is also connected, so 5 is also there some place. 1 to 8 is also there, so 8 is here. So you can see this is the connection. Okay, so this connection is there, so that actually make a graph. So in this graph now start.
It is directed.
Sorry.
No, so this is directed.
Now this is not a directed graph, this is an undirected graph. Well, let me check.
No, so there is below they have given the graph.
Okay, directed graph. Okay, so in directed graph, then
Yes, sir.
edge will be given, yeah, both side. Okay, 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 yeah, correct. So edge, yeah, you can see. Then if it is directed graph, it is mentioned here. Okay, no problem. So if it is directed graph, then it's still no problem, because the direction you can map that 0 to 8. Then you have to read only like this. So 0 to 8. So 0 to 8 means this way. Okay. 8 to 0 and 8 to 9. So 8 to 0, that means you have the different edge actually. In the graph, maybe it is written like this, but what directed graph means, you have the two different edge actually, 0 to 8 and 8 to 0. Okay. And here 1 to 3, 1 to 3, 1 to 5, 1 to 8. So 1 to 3 like this, you have to create the graph like this. Okay, if this is a directed graph. Otherwise, yeah, this, if it is an undirected graph, so definitely each entry should be filled by the two entry. Actually, if you have the edge like u to v, that means in the dictionary, u comma this entry you will get, also you will also get a entry for this u like this. Okay, so if graph is undirected, each edge will be represented by two entry in your dictionary. So here this is not the case. So 5 to 4 we have, but 4 to 5 we don't have. Okay, so yeah, this is the identification of the directed graph. Okay, so in this way we can just imagine this structure when we are dealing this data. Okay, now we have the 8 as a source node, starting point. Now 7 is the end point. Okay, end point. So we need to figure out a shortest path. Now in this problem, some algorithm is given. Okay, already algorithm is given, and we actually need to do some specific path. Okay, one second. So in this code, you can see BFS list path label. This algorithm is actually discussed in the lecture, and the purpose of this algorithm is also explained, that this algorithms return the information of labels. Okay, so we are just traversing each elements in the graph by the BFS algorithm. So that means the concept of BFS algorithm, and we are also defining the labels of the each node. Actually, which labels that node is coming. Okay, and we are also storing the parent information. What is this parent information? So label is this thing. So traversing is happening like this. Okay, this graph you can see. Now label is like this. So this first starting node is coming at like 0 label. Suppose we are assuming 0 label this. All the adjacent which are directly connected to this A, we will consider as a first label, because all these nodes are connected by one edge. Okay, now all the next labels nodes are coming at the second level. Okay, so this is the labeling actually. Okay, so how we are defining the labels adjacent wise. Okay, but another thing is a parent. Okay, during this process we are also maintaining the parent information when we are traversing the node. So that means if we are suppose A, there is no parent for this. Okay, so we are directly starting with this A, so that means we can write like this: A is a no parent. So like we can store like -1, or we can store some identification, and to understand that this have no parent. But after that, when we are traversing B, so definitely where from we are coming to B. Okay, what are the previous that adjacent node connected to this A. Okay, where from we are coming. So that information we will store in our some parent dictionary. Okay, so this is the key, and parent for this B is A. Okay, what is the parent for C is A. What is the parent for D is A. Okay, because all are all adjacents are actually from A, and we have already traversed A, and after that we are coming to B, C, D. Same when we are connecting this E, so E parent is actually B, F parent is B. Okay, so this parent information is very useful to identify the path. If you have this information, parent information, you can use the backtracking and you can identify the path. Okay, suppose let's G is that C and H is like D. Okay, so all this is the parent information we have this till this. Okay, now we want to find out the path from A to H. Okay, what is the path from A to H? So what we can do, we can start backtracking. Okay, so this is the end point. We will look what is the parent of H. Okay, so parent of H is D. Okay, so this information we will check from our parent dictionary. What are the parent of H? D. Now again check what is the parent of D. The parent of D is A. So you can see we have reached at the start. So we will start from the end point. We will check the parents, and we will repeat this process until we will get a that start node. Okay, so we have started H parent is D, so D is not still start node. Again, we will check. So a parent of D is A. Now A is matched with the start node. So this is the path. Okay, so this parent, using the parent information, how you can track the path. So this is the way we call it a backtracking. So that we will start from the end point. We will check the parent of that end point, and we will repeat this process till the start node, and you will get a complete sequence of the node in the path. So this is the first problem. Okay, now you have the code which is already given in your code. Okay, BFS list path level. So this is actually a BFS algorithm that actually maintaining parent information. You can see this parent of I. So increase this font. So this parent label is just maintaining a that label information, but we are not using this label in this problem. And parent is just only useful for this. Okay, so parent of I, and this parent of I, by the BFS algorithm process, we are storing the parent information. Okay, and after that we are returning this parent to the by this function. So you can use this function which is already given in the code, and here you need to write this minimum hopes this one. So that means you can call this function, you will get a complete parent dictionary. After getting the parent dictionary, what you can do, so you can simply just apply a backtracking on using the dictionary from this endpoint. Okay, so you have this endpoint already given. Just check what is the parent of end in the return dictionary. Okay, so return parent dictionary, what is the endpoint, a parent of this. So you can check the parent. What is, suppose this is x1. What is the parent of x1? Suppose this is x2. What is the parent of x3? This is x3. And in this sequence, you will reach at a start point after some time, because algorithm is called at the start. So definitely this will be the start point of the traversing. Okay, so your work is only to just do this process. You have the all data. You have the parent dictionary by returning one algorithms, and use the dictionary and just apply the backtracking for this problem. So I hope you know what is your work for this problem, and you can think about that how you can write the code. First thing is,
Yes, sir.
okay,
So can you
just
repeat the last part?
last point is
The parent.
so just start from this end point, read the parent. Okay, if parent is not equal to the start point, repeat this process. Okay, again check the parent of this point x1. Then suppose this is our next parent is x2, and this is also not equal to start. Okay, again repeat the process. And what is the parent of x2? In the x3. Okay, check this. At any point, if you reached at the start point, you can stop the process. So this is the path actually. Okay, you can write in the reverse way, like start is the first node, then this is the second, this is third, this is fourth, this is the fifth. Okay, in the path. Okay, now you have already one algorithm. You can call that algorithms on the start node, and you will get a parent dictionary with all data, and then you can write a solution.
But the expected output is the number of hops looked like.
So for this test case is expected output is 1. Okay. Yeah, so actually expected output is here 5. What is this? Why this is 5 we are taking here? Why we are not taking the path actually? Because maybe there is a possibility that with the same length more than one path is possible. Okay, so we cannot validate this solution with the path exactly, because there is a chance that if you write the algorithm in maybe different way, you are inserting the elements in the queue in some different order like this, so maybe you will get a different path where the elements are different, but definitely length will always be the same, shortest length, that cannot be changed. So here for this input 7 to 8, we are getting total 5 vertices in the path, including this start and end. Okay, there is a possibility that you will get another path in your graph with the same length. So, okay, and so because of that, we are not validating the answer with the nodes in the path. So that order may be, that path nodes may be different by the another path. So here we are validating by the number of nodes in the path total.
Sir, are we recording this session?
Yes, it is recording.
Okay, thank you.
Okay, so here actually you need to return a path. Your path may be different, but definitely your path will also be contain the same length, shortest length. And this 5 is not coming from your output. Okay, your code is return, your code will return a actual path, and suffix code is actually checking the length of that path which you are returning. Okay, so that is actually validating the answer. So now write a simple while loop type of code here. Here nothing is very actually this is now looks like a dictionary problem. Okay, this here you are not using any main algorithm. You are not writing a code for the main algorithm. This is looks like a dictionary problem now. You have some endpoint. You need to read the data from dictionary and just read the value, and again read the value as a key, check the corresponding value like this, and you have to reach to the start point. So this is the task. So just try to write the code for this. Okay, if any of you have any another approach, any idea, or you can also discuss now for this, and how you are writing the code, and you can also share your code for this, and you can explain this.
Hello, sir.
Yes.
So, what exactly the function is delivering to us? The initial function is given in the problem. Could you repeat that part?
Sorry, what you are asking? Can you repeat?
The what is the function is
So
explained?
that function, that minimum hopes. This you can see from suffix. We are calling this function.
No, BFS list part level function is here. Yeah.
This function is already given, and this function is actually saying that BFS is the BFS. This is the algorithm. This is the list algorithm. Actually, we are applying this BFS algorithm on the list, adjacency list, and this is returning a path and label information. So that is actually discussed in the lecture. This is directly taken from the lectures. Okay, so this algorithm is returning two information. First thing, this is applying a BFS on the V node in the graph. This is the V start point. After that, it is returning a label for the each vertex as well as the parent of each vertex. Okay, so you need to use this. So the first step in your function, just call this function and pass this start node as a this V node. Okay, and a list as a graph. After that, this function will directly return you the all parent information after applying the BFS. And this is a simple BFS algorithms. This is nothing new. If you will read after, if you know the concept of BFS, this is the actual BFS algorithm.
So,
Yeah, Bhumika.
so during OPP time also, like PFS and DFS graphs will be given, code will be given to us, or we need to write it.
It depends on the problems. Sometimes maybe problems comes directly based on the algorithms. Okay, so maybe you will get a problems that actually required a solution. Direct BFS algorithms code is required. So at that time, code will be not given. You have to write this code, algorithm code. Okay, this is straightforward algorithm. So you should know every algorithms, these basic algorithms at least. BFS. Okay, this working also. But if some additional task is required on the top of this algorithm, so in that case, this some algorithms will be given, and only the task part will be asked to write.
Okay, sir.
Hmm. So if anyone have done already, okay, so you can also share your code. Okay, so we will see your solution also. Someone is posted. Okay, so Devanshu have posted. So I will take that solution and check. Devanshu, it is working?
Yes, sir. All test cases passed.
Okay. So now you will explain this code, okay? Just wait.
Yeah.
Yes, correct. Okay. So just give more time for the others and you will explain. Prashant have getting some error. I'm getting traceback error. File data. Okay. So this is type error. You are trying to like this int object is not subscriptable. Okay, so it was a list. This is your code.
I posted the code.
Okay, 1 second. I'm copying this. Oh, it's not completely a structure. Hmm. So you have written this code. Min hope say list this one label and parent you call the function a list and start you passed label parent. Okay, shortest path list parent of parent is equal to I -1. First thing you have taken this parent. Okay, this is a dictionary, but after that you have taken the same variable name. So that means you have removed the dictionary or you have
Sir,
removed
when
the.
I change the name.
So this is the first thing. Now you have removed the complete data, and because of that you are getting this error because now this become an integer variable, simple, and you are trying to getting that reading like a dictionary for that. So because of that you are getting this type error.
So now when I change the name of parent, I'm not getting any output.
So then again, figure out that what your code is actually returning. Just take some small sample as an example and just apply the working of your code. Okay, just take some that random dictionary and see how that your code is working. Hmm. Yeah, so Devanshu have mentioned that you can use Python tutor to see the flow of your code. Yeah, this is also very good idea. So Python tutor is we have also added this Python tutor in our notes if you see.
Yes, sir.
Okay, so that you can see the step by step working also after running the code. Okay, next, and you can see how the data actually updated in this at each steps. So this is also very useful that editor you can use to understand the algorithms working. Okay, so same things you can also do here. You can take some data and just use this Python tutor to understand the each steps. Okay, now Devanshu, can you just explain in detail
Yes, sir.
what you did?
So first I took two variables s and e where I stored the start point and the end point of the uh, list which is given to us of the graph, which we have to start and traverse to end. Then I make two variables level and parent and store the level and parent which is returned by the BFS list.
Okay, correct.
So now, uh, since it is given in question, if the node is not reachable, then we just have to return the starting node. So first I check for that in level dictionary. If uh, we get the end key as -1, then we just return the start key. In the
Okay.
level dictionary, if our end key value is -1, that means it is not reachable, so we'll just return the start key. Else we run a while loop and check in the parent dictionary uh, if the end node is not equal to the starting node, we add that end node to our result list and then update the end node to the parent node of that node. So suppose we have 7 as our end node. So we check if it is not equal to the starting node, then we add it in the result list and we update e to the parent node of 7. So suppose it was 3, so now e will be 3. Now we'll check if e is equal to starting node. If it is not, then add the new end node to the beginning of the result list and then update value of e to the parent of the previous e. So in this manner we keep on adding the, I mean,
Okay, got it.
the
Yeah.
path, and then
Yes.
at the end we add the starting node in front of the result node and return the answer.
Yeah, correct. Very nice. Okay, so yeah, this is the correct approach as we have discussed. So this code is actually following the same approach. Now the things is this is just a writing style. So maybe if you are writing the code, if you are writing this the same logics, maybe you will write it in the different way something. So here, what actually this is the main part of this code. Okay, so this is actually traversing the path, complete path. This lower one part. Okay, so result is just a empty list. After that, starting node. This is S is representing a starting node, and this E is taking just as a variable. Okay, and what we are doing initially, we have checking that E is the end point here. Okay, and after that, we are just checking if E is not equal to S. So in the parent dictionary, yeah, so this one. So we are appending this. So result plus E. Okay, so that means result is empty. So we have added this as a first element in the result E. Okay, because we will append this every time parent into the at the first before. Okay, before the last node. So this will become like a E. Okay, this is the first node. After that, we will check a parent of E. What is the parent of E? And we will assign that value into the E. Okay, so the same things we are doing. We are just finding out the parent, and we are checking if our parent value is equal to start node. If not, then we will add that into a path like this. Suppose this is a new node. Suppose this is a x1. Okay, so this x1 is will be added like this. Okay, so x1 is now added. Again, we will repeat the process. If x1 is not is equal to s, then we will again, we have added this before, and then we will read the what is the parent of x1. So that suppose is x2. Okay, x2. Okay, now that will be append by like this. Okay, in this way. So we will repeat this process at after some times, after some iterations. So we will reach like this. So we will get a x2 parent is s. Okay, so in that case, this condition will become false, and our loop will terminate without adding this s into this, because we after checking the condition, then we are adding, actually appending before. So this start will not be added. So because of that, at the last we are adding this start, because it will not be added in the while loop. So then we will add this like a s. Okay, so this result list will actually extend like this. This will start from E, after that parent of this, then x1, then we will check the parent of x1. This is x2, we will check the x2 parent. If suppose this is s, so this will be added. And in this way, the complete path list will be created. And this is the actually path. This is now starting node, next node, next node to E. And this we are returning. But now the question is also mentioned that if suppose E is not reachable from S, so that condition we have also checked. Okay, that is possible only if our graph is actually disconnected. Okay, if our graph is disconnected, maybe two different components are there in the graph that are actually not connected. So in this way, maybe you will get a some parent information from E to like this. So E to x1, then x2. After that, if suppose this x2 is not connected from any node, and this is the like a totally separate component, and this is the top node of that, and this not contain the any parent. Okay, so you will get a the parent of x2 is now -1. Okay, because if any node doesn't have any parent, so that will contain the -1. So at any point, if you are getting -1 without reaching at the source node s, so in that case, you need to return a solution like a start only. So that is given in the question statement, not from our side. So return a list with only start node if the end is not reachable. So in this case, if you found this situation, so just return a start list. Okay, one list with start node. So that is the one validation we are checking here if we are finding this type of situation. Okay, so that things it is done by here. You can also did these things in the while loop. Okay, so during this process, if you are getting at any point -1, you can break the process and you can return start like this. Okay, so same things you can did done in the while loop itself. So yeah, this is correct approach. So same approach you can try by your own style. Okay, so just simply backtracking concept. I hope this is approach is clear.
Yes, sir.
Okay, so do not follow the code here. Just try to understand the approach and try to write your code, because if you will write your code, definitely later you can easily understand that your code. Yeah, so this is the first problem. Any query in this, any doubt in this, in the understand of the solution, or any other solution if anyone have done?
Sir,
Yes, Disha?
sir, could you please explain the last part, while condition?
This one? Okay. So, so let me explain this. So what actually it is doing. Okay. So what we are doing, we have some parent dictionary that is actually taken in this PRT. Okay, PRT, and this contain a dictionary like this. Suppose that one node is this is the first start node. Okay, that parent is actually -1. So start node, which because we have applied the BFS algorithm on S node. Okay, start I'm taking just as say. Okay, so that will contain a parent information is -1. After that, each adjacent like suppose x1 will contain suppose this S, x2 contain like this S, x3 contain like S. Okay, so all actually vertices will contain the like y1 contain like x1, y2 contain like x1, y3 contain like x2. So all are actually following this structure. So S, x1, x2, x3, x3, and then this one is y1, and this is also y2. So like this. Okay, so this traversing is happen in this way, and each vertices actually contain the parent information. So this parent dictionaries have this type of data. At one point we have also one E node. Actually, this is the end point. Okay, that have some parent like suppose x y2. Okay, y2. Suppose E is connected here. Okay, now what we are doing in this loop, so we are taking this E variable. So while E does not equal to S, so this E is actually not equal to S. Both are the different node. So we have taken this E because this contain the end initially. Okay, so the end is the actual data, but this is a variable. So this E actually contain the end. So E does not equal to S. S is representing a start, which is the actual value. So here we are starting from end, and in the list actually we are appending this as a first node. Okay, so E is added. Okay, E means end is added. Now, because in the at the first step, E is not equal to start. Okay, both are the different nodes. But what we will do, we will then append this end into a list because initially this was the empty list. This is the first added. After that, we will check what is the value of parent E. So parent of E is y2. Okay. Now this y2 is assigned to E. So E is now become a y2. Okay, this in this line you can see in this line we have assigned a parent value of E to E. Okay, so now parent of E is y2 and y2 is assigned to this E. Now we will check y2 is equal to start. No. Okay, now what we are trying to do, we are just moving from this leaf to root side. Okay, so E parent we have no y2. Now y2 we find y2 is not equal to start, then we will add before this. Okay, so y2 in our list in the that this step result equal to E. This is just a list extension. Okay, so we are writing like E equal to result plus result. So result is actually already end. Okay, and suppose this is a now y2. So now this are just a combination concatenation of two lists, so it become a y2 comma end like this. Okay, so in this way we are repeating this process. So after getting y2, we will check it is equal to start. No, then we will check what is the parent of y2. Okay, so now x1 will be append here. Okay, now we will check x1 is equal to s. No, then we will check the parent of x1. So that is actually s. Now s is equal to s. Yes, so this loop will actually terminate it. Now s is not added before this. Okay, that should also be added because this is the complete path from start to end. So the last step we done in the return statement, so that we are adding this plus s here before this. Okay, so s, so this become a s. Now this become a complete path in this way. Okay.
Okay.
Yeah, so these things we are doing by this while loop traversing. Okay, so suppose someone else also return. Yep, Prashant is giving the solution. Prashant, it is working.
Yes, sir.
Okay, so let me check your code. Okay, so Okay, equal to end. You have called the function. Shortest path list is empty. If parent of e equal to -1, shortest path list is equal to start. Okay. P equal to e. What is p? Shortest path. Okay. While p parent of e is equal to p shortest path list dot append, that is fine. Append. Append of e. So one thing, shortest path list. Okay, okay. But you are actually returning a list, correct? But yeah, you are not. You are returning a reverse list, reverse path. Because every time what you are doing, you are appending the parent in the end. So what you are returning actually end as the first node, and then next reverse path you are returning. But yeah, definitely it will also give the correct answer because we are checking the length actually of the path. So that is also okay to pass the test case. Yeah, one more thing. One actually, this is looking something in not complete this part because there is a chance that after this you have checked with only e. If e parent is -1, then you are returning a start.
No, sir. E is N.
E is the if you are checking if the parent of e is -1, then shortest path is equal to start, and you are returning this answer here because this will not work actually. But there is a
Checking in
possibility.
level would be better.
Because there is a possibility that maybe some e parent is there, but then parent is not there. In that case, your output will not be correct. A case like this, suppose you have this two actually structure in this. Okay, and suppose this is disconnected and this is now started here like this. Okay, so endpoint, and your e is coming at this point, and s is coming here. Okay, so what the output will be like, e parent is this one. Okay, now this parent is -1, then you will stop actually. But what you are doing, you are only checking for this e.
Sir, all the nodes are the minimum is
One
0.
second.
Like mine, there is no
Okay,
node
according.
called -1.
Okay, 1 second. Yeah, algorithm BFS is not performing the BFS only doing one time. Okay. That is also work. Okay, okay. Yeah, this is also fine because yeah, we are running only the one node. So if E is not reachable, definitely E will contain a -1. Yeah, so that is that is also fine. Yeah, yeah, that case is actually required when our BFS is running on the complete unconnected part also. Suppose if it is not reachable, then it will start from the another component like this. But this is not the case for this problem. So yeah, you can do this also.
Yes, sir. If there are disconnected component,
No,
it will.
your solution is correct. So because in one check we can also decide because end is not reachable, definitely end will be the -1 parent information. Yeah, this
So
is
in
correct.
OBB, there can be disconnected components.
Sorry?
Components then disconnected components in a graph, then this will not work. Sir.
No, this will work. Why this will not work? Actually, our BFS algorithm is working like this. So suppose this is the start node. So what it is doing, initially it is setting all -1. Okay, like this. And we
Yes,
are
sir.
starting a BFS on this. If this is reachable, the parent information will update for all these. But after that, our algorithm will stop. And these node, actually this side component will not be touched by from this algorithm, okay, from the
Yes,
BFS.
sir.
So all will remain -1 actually. And then we can directly check if he's -1, then we can directly return. Yeah, so your approach is also correct. Yeah, fine. Okay. Yeah, any other query, anyone? Now let's move to the next question statement, and I'll see the approach for that. Okay. Hmm. Back and forth. Yeah, this is also a one OPP problem. I think from the for the first term. Okay, let's. I'll just read the problem statement. Now I'll ask the approach from your side this time. Okay, and just think about that. We'll discuss. Write a function back and forth. A list end one and end two. Endpoints are there to return the maximum number of possible route between node end one and end two in the undirected graph without going through the same node again, with exception to end one and end two. The connectivity details between nodes are provided by the adjacency list. So now you can see for this graph. Now the problem is very clear. Suppose we are giving like 0 is the one end one, and this is the end two. Okay, this one. All possible path, maximum possible path we need to require here. Okay, so this is also one thing, a maximum possibility we need to require, not the all possible, maximum possible path. What is given? A maximum number of possible route. Okay. So in this way, if you see, so this end one and end two, how we can reach this? So you can see there is a one possible path like this. Correct? 0. I am writing here. So 0, 2, 3, then 1. Now the statement is given in the another path, we cannot repeat the intermediate node which we have already used in the another path already. Okay, but this is the initial point that we have to repeat. Okay, start and end. But middle nodes we cannot repeat in the another path. Now, next is so here what is the another possible path after this? Without using the same node again. So next possible path you
0
can
to
see
6 to 1.
0 to 6 to 1. Yeah, this one. Like this, okay? 0 to 6 to 1. Now after that, next is
0 to 4 to 5 to 1.
0 to 4, 5, 1. This. Okay, so this, and this one. This. Now after that, you can see no possibilities there.
So there's one more.
One more is there.
0 to 2 to 4 to 5 to then to 6 and then to 1.
No, this is what we have done now. See, we have used this 6 in 0 to 6 to 1. 6 is already used.
Okay, sir.
Okay, we cannot repeat. So we cannot repeat any intermediate nodes which is already used in the other path. So now this is the 3 possible solution for this. Okay. Now think about how we can approach this problem and which algorithms we can think here.
Sir,
Here,
suppose we
yeah, please go ahead.
suppose we take end one, then we check all the nodes reachable from end one, and then we check from that node if we can reach end two or not. If we can, then we increase count, or else we don't.
No, if you are so which algorithm you are applying to find this
Breadth
reachability?
first search.
Breadth first search. Why?
Sir, because it will search at level by level. So with each iteration, we'll be able to check. We'll be able to check if it is reaching towards one.
Okay. So my question is, why not DFS?
DFS will choose the longest path.
DFS, sir, DFS will cover maximum number of edge in a first time. So the possibility of getting the route
From
is
different images.
minimum.
Yeah.
Yeah, correct one. Okay, so because using the BFS, we will get a shortest path. So that will contain a minimum number of nodes in the one run. So there is a chance that we will get a more path. Okay, so here question is also asking the maximum possible path. And DFS maybe will give the longest path also. Okay, so maybe it will cover many number of nodes in the path. In only one path like this. Okay, so like it will maybe it will run like this. So 0 to 2, 3, 4, 5, 6, 1. So in one path all nodes are covered. Okay, but BFS definitely will find out a shortest path in the first run, and then we can think how we can update. So now this is the first steps. Yeah, that is fine. Here BFS is the good approach. Okay, so
So in
BFS.
DFS will not get many options, right? That is it.
DFS will provide a reachability or path. These things can provide, but there is no guarantee that it will provide a shortest path that will contain a minimum number of nodes elements. So you will not get a maximum number of path by the DFS, but by the BFS actually you will find out a shortest path every time. So that will contain a minimum number of nodes in the path. So in that way you will get a chance for the another possible path. So because of that we are thinking for the BFS here. Now the question is how, so you got a idea that BFS is okay here to find a path, but this is the one path. After that, what you will do?
So we
I
can
said.
put a visited list. Okay,
Mhm.
every time we visit a node, we can just label it as a true, and with the help of parent, we can traverse the end one to end two.
So parent, I'm not getting what you why how you are using the parent
So in the
information and why that useful.
in the previous question, like we have used the parent dictionary.
For path.
Yes.
Okay.
So so every time we just record an intermediate node that are used for reaching the end one to end two, we can label it as true in a visited dictionary. So
Mhm. Okay, and what question is asking? Answer total path is 3. Okay. And connectivity nodes are provided that number through. Okay, that's going through the same number of transactions. Okay. So here, yeah, this is the one thing in the path. Yeah, you need to find out a path also. Yeah, this is correct thing. So you have already done this part, how to find out a path. So that in the previous question, we know that how we can find out a path after getting the BFS algorithms parent information. So now that part is actually also required here. So because of that, I'm saying that if you have solved some one problem, so maybe some part of that problem you can use in the another problem. So now in this question statement, yeah, this is the first thing. What will be the first step for this?
Run a BFS from
Run a
N1.
BFS on end one. Okay, so they
End one.
suppose end one is the first point and two is the end point, last point. So you are running a BFS algorithms And there is a chance that BFS algorithms will provide a this path, like, okay, suppose this is the shortest one. Okay, there is another possibility 0 to 6 to 1. Okay, but I am assuming that BFS is providing this path at the first run. Okay, so suppose the parent of 3 is 0 and the parent of 1 is 3, like this. Okay, and so you will get a one path. After that, you can simply traverse like 1, then 3, and then 0. Now this is the first step. You got a one path. After that, what will be the next step?
Sir, 3 is marked as visited. So, yeah,
Ah,
so next time we cannot visit a 3.
okay. Yeah, this is the correct idea. So because according to the question statement, we cannot traverse the intermediate node which we have already used. Okay, except this 0 and 1. So we will only what we will do, we will only identify the intermediate node to mark that should not be repeat only. Okay, so 3 is should not be repeat after that. So yeah, some modification is required. Here you can see this BFS algorithm is given, and this is not given as a fixed code. This is given as a template code. So and comment is also mentioned here. You can update and use the following code in solutions. So that means you can modify this algorithm a little bit, and you can use the same algorithms for your purpose. So here afterwards, so suppose if you notified that this is the node which we have already traversed, then what will be the next step? Hello?
Yes.
So what will be the next step after that? So we have applied one time BFS on 0, we get this path, and we know that this 3 should not be come in the next path. So what will be the next step, and how we will remove this in the next path?
Sir, for that I have a different approach.
Mhm.
What we'll do is we'll take the end one and
Mhm.
find the uh, neighbor nodes of the end one,
Mhm.
and we'll perform a BFS on each of that. And if the BFS returns a visited list with true, if it reaches end 2, for end 2, if it returns true, then that means we have shortest path from 0 to 0 to that node and to the end node.
Okay.
Am
So
I
what
able
you
to
are
explain?
yeah, I'm getting your point. So what you are doing, you are saying that so find out the adjacent of this
Yeah,
one
we'll
is.
run a loop on this neighbors of end 1, so for 0 here.
So you are applying a BFS on this,
Yeah, first we'll
correct?
apply an BFS on 2, then
Uh,
3, then 4. No, for
okay.
not 4. 2, 3, and 6. We'll apply BFS on this. If end 2 is reachable from that node, then we'll count it, or else we'll not.
So in this case, what? So you are applying from the first step. So that means you are not. Okay, okay. Okay. So this is you're the first step. You are saying that, na? You are not
Yes.
including that what we have
Yeah.
done now.
Then we don't have
So
to keep track of the node
uh,
we have checked or
BFS,
not.
you are applying here. Okay. So now you are applying from this BFS. Suppose this BFS it actually provide a path information like 2, 3, and 1. Okay.
Yeah.
This is a possibility, correct?
Yeah.
And so to like 2, 3, and 1. It is provided reachability like this. Then still
Yes.
you have the adjacent this one, but this should not
Yeah.
be included actually. Okay, because now your previous run has already included this. So there is a chance that you are checking the path from the adjacent nodes, and they have the traverse the node which you are trying to traversing in the next step. So that means this things you have to check how you are actually identified that previous that intermediate node should not be come in the next path. How you are preventing this? your approach?
Then we have to put one more condition, that if the neighboring node uh, goes through the, I mean, suppose here 2 if goes to 3, then we don't have to consider that, and we'll have to traverse from the second next neighboring node of 2. Suppose it goes to 3.
That is the same thing we keeping record of visited or not.
Yeah,
It is the same idea.
yeah,
So
then we have
what
to
we
do that
can do
one.
is we just start from end one and end two. First time we get a path, and in all intermediate nodes will be marked as visited. The second time we can go through we when we find a new path, like in a first traverse we can go 0 3 1, right? In a second traverse we can go 0 2 3, but 3 is visited, so we can backtrack to 2, and then we can now traverse to 4. Okay, if 3 is visited and I am at 3, then we can backtrack to with the help of parent, right?
Hmm.
Yeah.
Yeah, so we can reach at 2, and now we can continue from 2 to 4 and 5, so on.
So you are saying that one BFS run is enough to identify all path?
Yeah, first BFS run. Then we have to do DFS for each
Oh,
node,
then it
right?
becoming more complicated then.
Yeah.
You have to write a DFS code then.
No, DFS is not, because it will block, it will, the maximum number of blockage, there will be
Hmm.
maximum number of blockage. Then we have to find the maximum number of paths, so we have minimum number of blockage in the sense visited node.
Here you can think about the multiple run of the BFS.
Yeah, multiple run of the BFS. Yeah.
Hmm.
We
Then
can keep
then
it queue. No, stack.
Uh,
Sorry. Can keep
no,
a stack.
you can take any list you can maintain only. Okay, so suppose if you run a first run, okay, on the BFS end one and end two. After that, just identify that which node actually traversed in this path in between. So suppose you are taking like this prevent list, okay, just including these three, and this data just passed into the BFS in the next run, okay, and same again apply the BFS on the same node. But this data should also be passed to the BFS algorithm, and because of that, this algorithm is given as a template. You can update this. So during the BFS process, what is the actually main concept of the BFS? Every time we check the adjacent nodes of the each node, and we check if they are not visited, then we traverse. Okay. Now we will add one more condition. If that adjacents are not in the present list, then we will only visit it. Okay, so this actually list which will contain a intermediate nodes uh, of the path which we have already included in the previous path, and that we will also pass into the BFS algorithms. Now during the adjacent checking or traversing in the BFS process here, you can see in this code, we will also include this list for the validation, that if our adjacent is not in this list, then we will check for the visiting. If it is already included in the list, we will skip because that is already used. Correct? So,
Sir,
huh,
what if we use backtracking with our end 2, that is our node 1, and
huh,
then we use backtracking like parent of 1 is 3
huh,
and 3 is parent is 0. So we
huh.
find a path and then we remove 3 from the adjacency list itself.
Yeah,
Huh,
yeah.
that
So
things you can also do.
And then
Yes.
we again make our adjacency list with, and then we'll have the parent of 1 to be 5.
Hmm.
Then we can again do the same thing, like the parent of 1 would be 5, 5 five's parent would be 4, and then four's parent would be 2, and two's parent would be 0. Then
Yeah.
again remove 5, and then again do the same thing.
Yes, that things you can also do. You are updating the data structure, that graph. So you have to remove all the entry which are connected to this three. Like suppose in the first step, this three is now we have used. So all the entry, that means 3 to 4 and then 4 to 3 also, because this is a undirected graph. So that means two entry will be there in the in our adjacency list. So that means 3 is a key and 4 is a value, and 4 is a key and 3 is a value in the dictionary. So every edge will be represented by two entry in the adjacency list. So when you are removing this data completely, so you have to remove all the entry like 3 to 4, 4 to 3, 3 to 1, 1 to 3, 3 to 2, 2 to 3. Then you can again apply the BFS from end one. Okay. Yeah, if you can do this, definitely your approach is also correct.
Okay, sir.
Okay, that
Sir,
will
one
also
more
work.
approach, if it is correct, I think, uh,
Hmm.
if we maintain visited dictionary at a global level instead of in the
Hmm.
BFS list path, the
Hmm.
function. So for the first time, it will turn. Suppose it start from 0, and for the first time, it will turn 3 to true.
Hmm.
Again, we'll run BFS on 0, and
Hmm.
if this time we get the end2 as true, then that means there's a path.
Hmm.
And now 2 will be also become true,
Hmm.
and then
Yeah,
again we'll run
yeah. So that
BFS.
actually, that is the same idea what we I was discussing actually. So you are saying the same things we can maintain like as a global variable. Yeah,
Yes, sir.
that is also fine. What I actually mentioned that we can pass this one additional list to the our each call. Okay, and we have to update our algorithms little bit. So during the process, so same things we can done with the global variable also. Okay, so what you can do, you can just make some list or dictionary what you are comfortable with. So like that prevent like a dictionary. Okay, and instead of dictionary you can simply use, because what why you need to dictionary actually for the visiting information, that okay.
Yes.
Yeah, that is also fine. You can create a dictionary for the each nodes like 0 1, but yeah, you have to maintain like this. This should not be included. Okay, so end1 and end2 should not be marked as a true. Otherwise, your algorithm will stop for that also. Okay.
Yeah.
Hmm. So 0 and this will always remain false. But after that, or initially we will set all false. So like 2 equal to false, 3 equal to false, and this we will use as a global. So after getting the first path, okay, so like 0 to 3 and 3 to 1. So 3 is now included. We will mark as a true. Okay, correct. It's true. And
Yes, sir.
still we have to update our BFS algorithm little bit. So where we actually need to update here, okay, we will use this global variable, and you can see this step for k in adjacency list if not visited. Okay, so this visited is the dictionary which is actually for the algorithm, but we will also add one more condition here: if not visited, and okay, and if not or we can say that if not that, what is the dictionary name you are taking? So prevent like this, uh, that or if not, okay, so one second, if
So the
so we
same
can
visited, we can make it as global.
no, this is for the different purpose actually. This is for the internal purpose of the BFS, and that we have to maintain for the elements nodes which are actually uh, already used in the previous path. Purpose is totally different. Otherwise, what will happen? Because 0 will also be marked as a present that visited. 1 will also be marked as a visited in the first run. Okay, so in that case, the next run will not run actually. So you have to maintain another dictionary or list like this. So if that prevent like this k, we are checking for k. So if this k is not actually true, Okay, we will get not here. Not prevent k equal to true. Then we will only mark as a true that we will perform this task. So what will happen if this k is already included in our previous path and this is exist in this list? So during this process, if not visited k and this, okay, if this comes as a in this dictionary, so we will not include it actually, or we have to write the condition in the correct way like this. So if we will only traverse if our prevent of k is equal to that false, like this. Okay, if not visited or this is equal to false, then we will enter in this condition. If this is true, then we will skip this path. Okay, so in this way our BFS actually will not consider this previous marked node during the process. That will skip, and it will return a totally another path, separate path, and that part definitely will not include the this 3 node, because this will actually not come into any possible path by this condition. Okay, so only this update we need require here. If not visited k and if prevent k equal to false. Okay, and then just entered inside this. If this our k is actually a not visited previously, then you mark as a true, store the information of parent like this. Otherwise, skip. So in the next run, now suppose we find out a next path like 0 to 6 and 6 to 1. So add this 6 into this global story or mark this as a true. So now the 6 will also become a true. So true. So again in the next run, again apply the same algorithm from the 0 BFS. Then that time this 3 and 6 both will not be included. Okay, because both have marked as a true. So in this case, that will be skipped, and you will get a totally new path. Okay, and what is the next possible path is only 0 to 2, 4, 5, 6. After that, you can see your all nodes are actually visited. Okay, so that algorithm will be stopped. So in this way, you can just how many runs you have done. That in that way you can maintain a count, and you will get a information.
Sir, so what we have to maintain extra thing?
You can maintain either a dictionary or you can maintain a list simply. For if you are maintaining a list, simply append these 3 into the list and just check here if that k not in this list, but only this.
Okay.
It change the condition. Okay. So during the that VFS steps where we actually check the adjacent nodes, and out of these adjacent node we check if which adjacent nodes is actually not visited. We only traverse that node. Here we will add one more condition if that adjacent node is not in the list, which is already previously visited. So both condition will be checked in, then only that node will be visited, otherwise not. So this is only one update is required in the condition. I'll just maintain even global list, or you can also add into the parameter, but global is also fine. So that will also work. So in both way, you can repeat this call process again and again, and you will get an answer. But
Sir,
here,
for the last end one, we should not make it as true. While loop.
so this end one should not be included in your prevent list. End one and end two should not be included. Okay. So this is the idea of this problem. Now, one part is just a path identification that is required. So that is the same thing which we have done in the previous problem using the while loop backtracking. After getting a one path, just find out a backtracking and then find out the intermediate nodes, include that intermediate node in this list, and repeat the process. I hope you have got some idea, or let me write a code.
Sir, I have written a code. It is working. Can you check it once?
Please paste in the chat. Okay. Oh, it is looking very small code.
And with this code, we have to do a little bit of editing in the BFS code.
Okay. So what editing you require?
So first, the visited dictionary that we have to create, we have to make it global instead of local.
Do not use the visited term then. Okay. So visited is already used internally.
No, I'm making that dictionary global only, so that I don't have to make any edits in the code.
But I think that will create a problem then.
Should I share the whole code with the BFS edited?
Okay. So yeah, just send me the code. Yeah, what you have done.
Excuse me, sir.
Yes.
Sir, could you please explain the problem statement once more? I couldn't understand it.
Okay. So here actually we have one graph. Okay. So that graph, there are two nodes are given, end1 and end2. We need to find out a maximum possible number of path from end1 to end2, or in between end1 to end2. Okay. And this is an undirected graph. And in each path, intermediate node should not be repeat. That is the condition. Okay. So in this example, you can see there are three possible paths: 0, 3, 1. We have the endpoint are 0 and 1. Okay, and 1 is 0 and 2 is 1. So in between these nodes, how many maximum paths are possible? So there is one path possible: 0, 3, 1. Now next path is 1, 6, 0 or 0, 6, 1. We can read like this. Okay, and 0, 2, 4, 5, 1. So in all these three paths, you can see intermediate nodes are not repeating any. Okay, so we are not using any intermediate node in the another path. So all three are the totally different path. So
sir, but why not 0, 2, 3, 4, and then that path? Why is that not considered?
Sorry, 0.
0, 1 second, 1 second.
Uh-huh.
0, 2, 3, 4, 5, 6, 1. That's also a path, right?
1 second. So you are writing. Sorry.
I mean all the circular way around. Even no node is repeated.
How the pointer will be small actually. Okay. Oh, my marker is now big actually. Some setting is there. Okay, so you are saying I'm typing now. 1 second. This problem WeeK-4 live code. Here will have a right pen perfectly. Okay. So you are saying that one path you are taking. Can you repeat again? 0,
0, 2, 3, 4, 5, 6, and 1.
5, 6, and 1. Yeah, this is one possible path.
But this was not considered in the answer, right? There were only max possible routes were 3. The answer was given as 3, you know, sir.
No, suppose you are getting this path as a first one path, okay?
Okay.
But any another path possible then?
No, sir.
So we found only one path. The
Okay.
question is asking maximum number of paths.
Okay. Okay.
Okay. So our here target is also
okay
to find out the maximum number of paths.
Okay. Okay, sir. 1 second. Sir, what about the path? The answer they have given 02451.
02451. Okay. Then
Hmm.
so
So
you are
then
getting
what?
the same one, no? So you are getting the same thing. So after that, next possible path is
What is
zero
the
three
next one?
one. Correct?
Yes, sir.
And next is 061. So same we have discussed now. All three
Oh,
paths
okay,
we have
okay.
discussed.
Okay, next I should not visit the same node. Two should not be visited again.
Uh,
Okay, okay. Now I get it, sir.
okay, okay.
Thank you, sir.
Yeah. So okay, the ones we have posted. Okay, Devanshu, so your code is working?
Yes, sir. It passes all the test cases, private and public.
Okay, then let's check. Okay, so you are using this wasted globally.
Yeah.
Okay, and then you have. Oh, second. So you are using this wasted. And what? This is your back fourth algorithm. Yeah, count equal
Yeah.
to 0 and listed and 1. VST VFS last list. If VST and 2 is count.
Uh, Sorry, in the chat, a line is missing from my code. After that count plus equal to 1, then we have to do VSTD and 2 equals to false.
Can you repeat next
In the
slide?
next line, VST V, sorry, B, not B, V, VST.
V.
Yeah, VST, square bracket,
Uh,
end 2 equals to false. Yeah.
okay. Okay, so you are updating VST. So VST is here.
No, that is the variable taken in the uh, backend fourth.
Okay. Visited. Here dictionary name was here, and this is VST. Okay.
Yeah.
Okay. Fine. So what you did this first thing count equal to 0. I in you call okay. I in adjacent list and 1.
Yeah, for all the neighbors of the end one.
Okay, and you are calling the that algorithm BFS.
Yeah.
Okay. If VST of end 1, this is the if it is true.
End 2. Yeah, if we get that true, then we increase count.
All the VST algorithm on I each adjacent. After that, you check that N2 is reachable. Like, and you increase the
Yes.
count. VST
Since
and
the
then
N2 was reached, so we again convert it into false so that for the next iteration, we don't get it as true already.
okay. And what update you did here?
Just did the visited to global instead of local and nothing else. And yeah, from BFS, I in the return statement I removed the print parent because I didn't needed that.
Mm, okay, apply the BFS. Okay, so I'm not sure. So here maybe it is working. So to check the some
That return statement is out of the so that false is capital M.
past. Okay. So let me think about your approach. Maybe any corner case. So like this is, suppose this is 0 point, this is 1 point. So you are checking the all adjacent, like, okay, adjacent, like this is A, B, C. And we have the path like this, okay, C, D, B, C. Mm. So for this type of case, suppose this is a N1 and this is a N2.
Yeah.
How many paths your algorithm will return?
For this one, only one.
Why? So because when you there are three adjacents are there, na, correct? So A,
Yeah.
B, C. Okay.
Yeah, but suppose for the first time it runs for A, then the this path of the nodes that are getting true are A, D, E, and F, right? So next time when it goes for B, it will turn B to true, but uh, then it will check for just a second.
I'm getting your point. Yeah, correct. So in this path, if all this is marked as a true, then next path
Yeah, then
you
it will
cannot
not enter.
from
Yeah.
enter in this. Okay, so because of that, you are getting the correct count. So this is the one. Okay, it's the correct things. Another possibility. Okay, so 0 is 1. So this is another possibility. Then looks like correct. And suppose we have like IFH. Yeah, looks like correct approach because it is also fulfilling the correct criteria, and looks like it is more actually uh, like efficient solution. Okay,
Yes, sir.
because in one run, you are not one run, we are checking the multiple run, but yeah, definitely. So we are calling 3 times.
Yes.
Okay, and we are running a algorithm. Yeah, so in this case, looks like suppose this is depends on the number of adjacent nodes. Suppose if we have like this 0 and we have many adjacent nodes at the first level, like 1, 2, 3, like 100. And then
Yeah.
after that, all are coming from the one path like this. Okay.
Yes.
So in this case, still your algorithm will run total
Yeah.
100 times.
It will run, yeah, 100 times,
It
but
will
it
call 100
will
times.
count only one.
Yeah, it will count only one. Year. It will return the correct answer. I am just trying to understand the that efficiency, okay, of the code. Okay, so it will actually now it is totally depends on the number of adjacents. Okay, so in this case, if a large number of adjacents are there, so some that wastage calls are there because you find out this in the first one steps, and after that all are recursive. But yeah, approach is fine. Yeah, approach is looking correct. I'll also check later if any corner case is maybe missing or not, but looking like will not it will handle correctly. So, but yeah, if
Okay, sir.
approach is correct. Okay, yeah, nice. Yeah, so this actually very small code, small approach. Otherwise, so what we are discussing actually, that is also similar. So we need to done, yeah, so you are not actually calculating the path. Actually, that task you
Yeah.
are now reducing. So you are not checking the path traversing, all these things. You have reduced that parts. That is the fine thing in this code. Otherwise, we have to traverse the path and then we have to identify the middle nodes. So that things actually reduced. Yeah, this is nice. Mhm. Yeah, this code is, I hope everyone get this approach. This is straightforward approach. In the what we are doing actually, we are just looking from the each adjacent nodes, okay, and each adjacent nodes and calling the BFS algorithm and making the visited dictionary global. If first run, how many intermediate nodes are actually become true. So next run actually that will not automatically consider because that is already visited. This is happening because of global dictionary, that global visited dictionary. Okay, and because that will remain updated in the each call, will not change. So this is one benefits of this global dictionary. Yeah. So any doubt in this approach, anyone? Another approach is we have discussed is that is actually run a BFS algorithms, and that one have discussed like that, remove the information from the data structures. That is also one possible solution. Another is just maintain a list of for the node that is already visited in the path and do not touch that node again in the next call. Okay, after updating this BFS. So that is the one possible solution. This is the another possible solution. So all three approach we can use here. Any doubt in this approach?
Sir, if
Anyone?
you use a prevent dictionary, then we'll have to use run this BFS algorithm until all the elements becomes true, except end one and two.
No, what we will do actually using the prevention list or something like this, we will run a while loop, okay, and we will just perform a this which call BFS call every time, but we will update the BFS list algorithm for the condition, and we will run this if we have the any node is remaining in the path, that graph, that number of time while. So we will just maintain some condition. So like that visited end. So let me think about the condition for the stop. While visited end.
And sir, can you explain the def back and forth ones?
Uh-huh. Sorry? Are you asking for explanation?
Yes, sir.
Okay. So regarding that, so the previous approach which I am discussing, that we will run a while loop, okay, and we will in the every run we will check if our end 2 is reachable, okay. So then we will find out the path and then we will get a new path. If at any point our path is not, that end 2 is not reachable, we will stop the process because that is the last point to identification. So that is just that is one benefits of that our approach, because in this solution we are running BFS algorithm at the number of time of the adjacent nodes of that first node. If that adjacents are 100, so our algorithm will run 100 times. But in our approach, that we will check that if our that things you can also check, I think. No, you cannot check. Okay, so in our solution approach, that our while loop will stop at the first point if our end2 is not reachable. So okay, so first thing, discuss this approach. Someone is asking like, so what we are doing actually, we are so this is the back and forth function end1 end2. We are making this count equal to 0. Now in the BFS algorithm which is given in the question statement, we have updated little bit. We maintain a visited dictionary, okay. So visited dictionary as a global dictionary. So this was actually a included in the code inside the function itself in the previous code. But what we did, we just make as a global, So now this is not depends on the each call actually. Okay, so that will remain as updated in the each call. It will not reset. So what we are doing in the first call, in the what we are doing for the each adjacent nodes of the end one. By this you can see for I in adjacency list value for end one. So that will return all adjacent of the end one. Each adjacent run, we are calling a BFS algorithm on that. And after that, we are getting a visited dictionary as a return output, and we are storing that in the VST variable. And our N2 is reachable from this point I. Okay, so I is already connected to end one to I directly, and now I to N2 is reachable. That means one path we found, and we will increment our path count here. And we will again reset our N2 is not reachable. Okay, for the next checking. Then again this loop is running for the second adjacent node. So if we are getting the same type of behavior, that means if our N2 is again reachable, so definitely that will be reachable only through the different nodes, because our BFS algorithm is checking this visited dictionary. So if it is visited by the previous run, so that will also be stored. That information is also stored in this. So this that nodes will not be considered again. So in the second run, we'll actually check a new path totally without using the previous path, that nodes. So if you suppose if you found another possible path, so it will return a reachability value true, N2 is equal to true. Then we will increment our counter again. So in this case, we can repeat this process and we will get our total different count path possible. Okay, in this. So that will return a correct answer. So this is the one approach. Okay, so as we have discussed in the graph, so let me discuss here how it is working actually in our that question statement problem in this graph. Let me copy this. Okay, so how this code is actually working. So what we are doing, we are marking visited equal to false at the each nodes. Okay, so suppose this is false, 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 all false. And we started the BFS on this node, so this will come in true. Now after that, what we will apply a BFS run on this. So in the first, that BFS will find out a adjacent node. So that is the which one is the adjacent 2 and 6. So 2, what is the next knowledge is. So in the first run, actually, it will provide a one possible path. So this okay. Okay, no, we are not doing this. We are calling a BFS on the adjacent node.
Sir, we can call at the end one also. That will also work.
No, that then it will not work, I think.
I checked it was working.
No, suppose if we run this BFS algorithm here.
Yeah.
So I think all node will mark as a true.
No, for the first time, it will only find the shortest path.
No, we
Okay,
are.
yeah. For it will mark all the nodes as true. Sorry, sir.
You know, so that
Yeah.
this become true, this become true, this become true, this. So how that will run again?
Sir, it on the adjacent node it will run. For 0, first it will run through 2, then through 3, then 6, like that.
Mm. Then it's looking some problematic here. Suppose if we are running that on the adjacent nodes also. Okay, so suppose we are running from
Yes.
this BFS. So
Yeah.
from this node also, all should be marked as a true by the BFS.
It should have been, but it is not marking.
Oh,
First, it marks. Suppose it finds the shortest part. So first, it marks 3 as true, and then it goes on for the next node of 3, which is the shortest.
no, how this code is actually preventing this?
Due to the fact how BFS is written.
No, BFS is actually finding out the all actually connectivity, not only the one. Okay, so BFS actually checks the all connectivity. So if you are running the BFS here, so that it will check the all node connectivity from this. So that will
Yeah.
become like a two. Then you can reach from the three also. What are the other adjacent? Four also. Okay, so
Yes.
this is now first visited. Uh,
Yeah.
as well as this zero will also be visited if you are running from this. Okay, so
Okay.
in this case, next is now that from three this one is also visited, and any other another node? No. The four from 4 5 is also visited. So all will become as a true actually, na?
It should have been, yeah, but it
Huh,
is not.
but the next run, how it is actually running? Then it is looking like maybe corner case fails. So here you are finding three possible paths because you have the three adjacent nodes.
Okay, because we are running BFS again. So that's why, since the initialization part, it turns every other node to false again.
Where it is?
In the BFS code for the initialization part for I in a list, it turns all the nodes to false again. That's why.
But then your global dictionary. We have to think about that some corner case for this. So
Yeah.
I'm not getting that the correctness because you are also maintaining this state dictionary globally as inside this you are also resetting this as a false. So global state is equal to true. Next run. Okay, so I'll also check this. Also, you can try to think, maybe looking
Yes, sir.
like it maybe fail some in the some case. Okay, try to
Yeah.
figure out that the corner case because that purpose is not fulfilling, which we have discussed by this
Yes.
algorithm. Okay, so then I'll explain our approach. So anyone have done that another approach?
Sir, I tried, but I'm getting some error. I'll check that.
Okay, so I'm removing this. So any other change we have done in this code apart from this wasted?
No,
Devang?
sir.
No, no,
No,
that
sir.
template code actually. Yeah, only. Okay.
Yeah, that parent.
Hmm. Okay, so you just validate this. Look, okay, so I'll also check later this.
Yes, sir.
So what other things we can do? We can maintain some that global list. Okay, so that let me just remove this. Right. Okay, so like prevent, or you can make this as a global, not required here. So outside of this, okay. Prevent equal to simple list I am using here. Okay, so prevent list, and inside this function, then I'll check only. We will take some counter here, so to just find out a number of calls we have done. So that count, and that we will call our uh, function. So that DFS list, this one. Okay, and we will read the data what this is returning. So here actually we need a parent information only. So okay, that visited is not required. Hmm. Visited we required or not? Okay, not required. Parent information is only required. So okay, what we are returning? Okay, so you have also changed, I think, here little bit. Look like parent.
Yeah, I removed that parent also.
Parent. Okay, so that I will write like I say v comma p equal to parent. Okay, so now this is the first call, and we will get a shortest path in the parent p. Okay, so that p. So now after that we will run a loop. So while and how many times we will perform this loop? Actually, if we are getting a reachability to the n2. Okay, so if our n2 is reachable, we state that if our that v n2 is equal to that true. So if this condition is true, then we will repeat the process. Okay, so because we have reached at the our n2 in the path, and in this condition we will now the next step is, so okay, so now our n2 node is reachable, so we will increment our counter 1, and okay, now the next step is path required. Because we need a path. Actually, without getting the path, we cannot identify that which node is actually used. So that means we need a path. How we will get the path? So that previous code actually here we can use. So same things we can do here. So how that we will do? So what we can do? We can write like a that we can create a list. So like path equal to empty list, and then we can just perform the same things. So from the end actually. So what is the end? We have end 2. Okay, so we will take some variable here. So like e equal to and 2. Okay. Okay. So now we will just use a reverse path thing. So current equal to, so what is the parent node of this? And okay. So that is current. Okay. So we need only intermediate nodes. So no need to check that and to all these things. So what we can take current equal to parent of this, parent of, sorry, p of that e. So that is the parent information, and that things we will add in our path. So path dot append equal to this CURR. After appending this, we will update our current to parent of p of current CU. Okay, so this way. While current is not equal to start. Miss some path equal to 0. We need a here step while CURR does not equal to and 2 and 1. Hmm. So this condition should become here. Okay. So what we did actually, while this v and 2 actually is equal to true. So that means we are getting a path true. Okay, so we are finding out a reachability to the n2 point. Okay, so that means we get a new path and we increment our counter by 1. After that, we are finding out the path actually. Okay, so path is equal to empty list. Now E is the just a point like n2 point, and then we will start what is the parent of E. Okay, n2 that we are storing in the CURR, and then while CUR does not equal to end1, end1 is just a start point. Okay, so in this case we will append this CURR to our path list. Okay, and CUR we will make, we'll again find out the parent of this CURR and we will update our CUR. So this will repeat actually completely, and it will find out a all intermediate nodes between end1 to end2, and that nodes are now added into a path list. So this path list actually we need to append in our prevent list. So all the nodes should be append in this list. So that means the global variable. Instead of this, we can directly append this into prevent dictionary. That will also fine. Prevent in this prevent dot append. That this is not required. So now this is the while loop, it is done, and after that, okay, and then we have to again call our this. Okay, so now this is the first step. You can see again we call the same algorithms inside this while loop. So we call the same algorithm again, and it will return again this v and p, and we will again check in the while loop. So if we are getting the same again true, and then we will do the same process. We will increment our counter, and e equal to n2. So we will set this. So all things we will repeat again. So here this okay. So we have to also update our list here. So that condition here, if and k like not in, if k not in, that what is the dictionary prevent this one, then we will only mark which is equal to true. So let's check.
Sir, for BFS list path, we don't have to give end1 as the input.
Which state is equal to dictionary. Oh,
no, not this one.
1 second. Actually, I make the C comment.
We are not initializing visited in the BFS code.
No, it is there now.
No, I mean we have to initialize visited as a dictionary and as an empty dictionary, right, inside the BFS path code.
Okay, okay, that is removed actually. Yes. Okay. And what local variable we reference before assignment? We where we used?
V inside the v comma p equals BFS list path.
We are not using this. No, v is equal to visited. Okay.
No, not there. In the arguments that we are giving for BFS list.
Oh, this one.
No, not this one. Inside the back and forth. Yeah.
Oh, this is actually a that end one.
End one. Yeah.
Hmm. And this is also end one again. Okay. And then we are not returning anything. Okay, 1 second. So return C. Okay, now just case. Okay, so this is one approach that we have actually discussed. So what we are doing, I hope this is the same we have discussed. So we are calling the first time BFS algorithm. Then we are checking our N2 is reachable. If yes, we have increment our count. Okay, and then we find out a path actually. Okay, so in path we are only focusing on the intermediate node. So because of that, we not included the N2 point in our that path. We have started we have included our intermediate node in our prevent list. Okay, so you can see this prevent, we have appended all the list. After that, we again call the BFS list. And why we are using this prevent? Because we will not include again that node in the traversing. We have updated this condition in the BFS algorithm. Okay, and so in the BFS traversing, if our adjacent k is not visited or not in the prevent list, then only it will be traversed. Okay, it will be marked as a true. Otherwise, it will be skipped. This part will not be done. So next call, that previous intermediate node will not be included for the consideration. So in this case, we will get all the path at any point. If our N2 is not reachable, this loop will actually break. Okay, this condition will become false, and our loop will terminate, and we will return a final count here. So that will actually return a total number of count path actually possible. Okay, I hope this approach is clear. Previous approach was looking correct, but looking like some corner case maybe failed. We will check that also. But this is, I think, fine. Any query in this approach? Overall idea what we are doing?
No, sir, it's clear.
So let's move to the next, third one. Okay, so now just read the problem statement and think about that which approach here we can use. So cool worker. So this is also, I remember that this is also a first or second term OPP problem. So the group of workers have to complete a list of tasks. Those tasks have dependency within the task list. Okay, but the worker prefers some interesting task and hates to do some boring task. They always do the most interesting one among the available tasks to be done. Okay, so now this is just a scenario. Write a function cool worker where the a list, that adjacency list, is given preference. There is one additional list is given here uh, to return the order in which the task will be done. Adjacency list is the adjacency list dependent with the dependency, and preference is the task sorted in the preferred order, in which task and index 0 is the most preferred and index -1 is the last preferred. Okay, yeah. So here actually some dependency is there. First thing is the dependency. So you can think about, if dependency is given, So which approach or which type of algorithm we can use for the dependency?
Topological sorting.
So dependency means if we will create a graph for that, so it will become a DAG actually, directed acyclic graph. Okay, dependency type of problems. So like dependency type of problems, you can think about the topological sort approach. Okay. So here also topological sort approach is required because that adjacency list contain a dependency. Like what type of dependency is? So this 1, 2, 3, actually that 1 in this graph 1, 2, and 3 are dependent on 0. That means 0 should be finished first. Then you can only do 2, 3, and 1. Okay, so that previous like as a that core requisite or prerequisite in your that program BS program. Okay, so you cannot do med 2 course before without completing the med 1 course. So that type of dependency is there. Okay, so similar type of that you cannot do Python course without doing the CT course. So some dependency is there. If you will just make a graph for this dependency by just connecting a directed edge. So you will get it DAG actually, directed acyclic graph. There will not be a cycle on that. And then that type of problems can be generally asked like what order you need to complete that. So what type of graph will be created like this? So this is the dependency problem, and this is the dependency like okay. So 1 and 2 and 3 like this. Okay, so 1, 2, 3 are the dependent on 0. Okay, so like then 4, okay, then like this, and 5 like this. Okay, and then suppose 6, and then 7, and then 8. Suppose this type of graph you are getting. So how we can do this task actually, because we cannot directly complete this one because it is depends on the 0. Without completing the 0 we cannot complete this one. So first we have to complete this. Okay, 0. Then dependency will be removed. All this dependency will be removed. Now this 1, 2, 3 will be available without any dependency. So then we can do these. Okay, 1, 2, 3. If we have the enough resource, we can do parallel all at the one step. Okay, so like suppose if we just consider as a course. Okay, so this 0 is the one course, 1, 2, 3 is the course, 4, 5 is the course, 6, 7 is the course, 8 is the course. So 1, 2, 3 course we cannot done without completing the 0 course. Okay, but if all the courses are available without any dependency, we can do in the parallel in one semester like this. So how many semesters are required? So this type of question is also important for the quiz actually. Okay, so this type of information will be given and will be asked like that: how many minimum semester is required, how many minimum module is required, like this. Okay, scenario based. So in this case, we cannot complete 1 to 3. We can complete at one semester like 0. Okay, so this is the first semester. But after completing this, now this 1, 2, 3 is available without any dependency. So that 1, 2, 3 we can do in the second semester. And then after completing this, all dependency will be removed. Then 4 and 5 we can done. So this is the third semester. Then 6 after completing this will be in the fourth semester. Then fifth semester. So in this way we can figure out the our completion order. So the problem is also very similar. Some dependency is given of the work, but what happened actually, it is asking that what will be the order of, and some preference is also given. So input is given like this, but if suppose sometimes more than one task is available to do, then we have some preference. Suppose list is given like this. So 0, then 2, then 3, then 1, then 5, then 4, then 7, then 8, then 6, like this. Okay. So in this way, some preference order is also given. So this during the topological sort, we will do the same process topological sort here, but after completion of this 0, okay, because here we have no choice. We can select only one. So in this case, we will select 0 only. But after that, we have choice now, 1, 2, 3. Which task we can done first. Then if we have any choice, then we will check which have the higher preference in this list. So which one is coming first? Okay, so 1, 2, 3. So you can say 2 is coming the first. So the index is like 0, 1, 2, 3 like this. So 0, 2 is coming first. So this is the highest preference. So that means this will be selected next. Okay, so 2. And next step is now after doing this, this edge is removed. Still 4 and 5 is dependent on 1 and 3. So 1 and 3, which one is the highest precedence? Then we will again check. So 3 is the highest precedence. So 3 will we do. So now 3 will be removed. Now 5 is available. Okay, so now 1 and 5. So 1 and 5 is available to do. So in this case, which one have the highest precedence? We have to check. So 1. We will select 1. Then after selecting, then 4 and 5. So 4 and 5 again we will check. So you can see 5 will do. So after doing 5, 5, this 7 will also be available. So 4 and 7, which have the highest precedence? 4. So in this way, we have the problem. So we have this adjacency list graph, and we have this preference list. Now apply the topological sort, and during the topological sort, just do little bit update in the topological sort. At any point, if you are getting more than one node without any dependency, then check the preference from this list to select the node. Okay, this is the additional task. Topological sort algorithm, what you have learned in the content, that same you can use. Only the update is required, this preference list checking part.
So we can not use the longest path.
There are two algorithms actually, longest path. Yeah, that first one you can use, I think. So
like if 2-3 nodes are there in the same level, then based on preference we can do.
That you have to select the node preference based on the preference level. So that so this one you can see the topological sort. So where actually you need to update that part actually is required. Topological sort. Okay, so this algorithm, this one algorithm, topological sort. So what actually we did in the topological sort, we always we actually maintain the in degree. Okay, in degree, and in degree, if any node have in degree 0, in degree 0 means there is no edge coming on that node. So that means all dependencies now removed. So we consider that node for the next consideration, next like a traversing. And sometimes you will find out that you will get a more than one nodes with the 0 in degree. In that case, you have to check the preference list to select next node. So here you can use the same this topological sort algorithm and in degree. So after removing the node, you have to update all the adjacent nodes and you have to reduce the in degree 1 to the each adjacent nodes after processing. Same things we are doing in this algorithm. You can see in degree we are maintaining in the dictionary, topological sort order we are maintaining in the list. So 0 in degree we are maintaining the queue actually. Every time we will include the 0 in degree node in this queue and we will read from the queue. So from this you can see we are just traversing. This is the initialization part. First we are setting to all in degree 0. After that we are reading the graph data structure and we are setting our in degree according to the graph. This is the part. Next step, find the vertex with in degree 0 added into the queue. So this is the step we are just getting the in degree 0 nodes in the nodes. But at this time, if you are getting more than one nodes in the in degree 0, you have to check into the preference list which actually is coming as the higher precedence. That will only add it into the queue first. Okay, so in this way you can update this code little bit. Otherwise this will remain the same and your topological that list will be generated. Okay, so you will get a order correctly, this one.
So but how do we check preference?
So you according when you will get a in degree nodes, then you have to find out the index. Actually during according to the index you have to identify that.
In this if conditions.
So if condition, so that preference list have some index now, so that list is given like this. So index is like this 0 1 2 3 4 5 6 7 8 like this. Okay, so what you can do, you can just identify the index that 2 have the 1 index, 3 have the 2 index. So in which way, which one have the smallest index, you can identify that corresponding value you can use first. Okay, so that update is only required in the topological sort. Otherwise, the problem is very straightforward based on the topological sort directly. Okay, so how you can find out the index things are like the preference. What you can do, you can make a during the, suppose you are getting like 2 3 4 for the next step. Okay, now you can make a list. Okay, you can make a list, empty list, and just identify that what is the index of 2. This is 1. Okay, so this is you can make it tuple like 1 and 2. Okay, append this. What is the index for 3? This is 2. 3. Okay, and what is the index for 4? This is 5. Okay, so 5 comma 4. Just make a list like this, sort this list.
So can you repeat this?
What you can do to getting a node which have the highest precedence. So for this example, okay, so this is actually 0. So 0 adjacent that after removing the 0, you have 3 nodes, 1 2 3. Okay, so 1 2 3, 1 2 3. Now you need to find out which node have the highest precedence. So how you can identify this? So this list is given where you have the all index. Okay, so you can easily identify that index by just direct index function. Okay, so like L dot index of the value like 2. Okay, you will get a index value.
That is preference list.
From the preference list, yeah, preference. Okay, that list. So, but how you can actually, you have to identify the highest precedence based on the index value. So you have to create a, you can create a list, empty list, and just find out the index for the 1. So 1 index is 3, and make it tuple. So index first and value second value. Okay, make it tuple and append into this. Okay, so in this list 3 and 1, this will become a first. Okay, now identify the index for 2. So index for 2 is 1. Make it tuple and append in this. So 2 comma 1. No, index first and value at the second 2. Use the index as your first variable in tuple. And what is the index for 3? This is 2. So 2 comma 3. Now all nodes are done. So now sort. Suppose this is a new list L. Okay, now L dot sort. Now this sort will done actually based on the index value. So this will come as a first. So 1 comma 2, and then 2 comma 3, and then 3 comma 1.
Sir, but if
Use
1
this.
is a prerequisite for 2, then we can't do this.
1 is a prerequisite. No. Here we have already picked the node which we can actually select because dependency is now removed. Okay, so 1, 2, 3. All these are available.
Same level.
All actually are now, there is no dependency. At each time, suppose if the first time only this 0 node is available with in degree 0. Correct? So we will directly pick without checking the preference list. But after selecting this, all edge will be removed. Okay, now the dependency of each adjacent will be reduced. Okay, so now this in degree will become 0 for this, 0 for this, 0 for this. Next iteration in the topological sort, these 3 nodes are available in degree 0. Among all these nodes, you have to pick the nodes which have the highest precedence according to the problem. So 1, 2, 3. Then we are finding out the which one have the highest precedence in the precedence list. That we can only do by the indexing. Okay, which one is coming at the first that has the highest precedence. Okay, so that we are trying to do here. So what we are doing, we are just finding out the index of each and making as a first element in the tuple, creating a list of tuple, then sorting, then picking the first element as the highest precedence. So this is actually a this 2. Okay, so now this one, which one? 2, yeah, 2. Okay, this one have the highest precedence. That we will select for the next iteration in the topological sort. Okay, so we will remove this from the list, and in the next process, if our any another node is also getting 0 in degree, that we will append in this and again sort this. Then we will pick the first element. So in this way, you can do this preference selection.
Sir, also if we do 2 and 3, then 5 will also have in degree 0. Then
So after
we have to
select,
check difference between 3 and 5.
so 1 second. So what we will do, we will select. We have selected 0 in this previous example. Now we will select it 2. Okay. After selecting 2, you can see this edge will be removed. So after selecting 2, this edge will be removed. Still, this 4 have in degree 1. Okay. This is still have in degree 1. Okay. After removing, we cannot pick this. Then we have to select the next smallest element. So that is actually this one, 3. Okay, this is the indexing actually. First value is representing indexing. This is the actual node value. So 3 we will pick next. So after picking 3, so this 3 picking, that means this edge will remove. Now this 5 become in degree 0. So we will add the index of this 5. So 5 index is 4. So that we will add in our list, which is actually now only contain this. So that means 3, 1. And we will add like 4, 5. Okay, so this is the index and this is 5. Now again we will apply a sort, L dot sort. So after applying a sort, the first index which have the lowest index will come at the first value. Then we will select as this one node as a next element. Okay, because this have the 3 and 4, this is the smallest one. Now after selecting the one node, so that this is also removed, so 4 will also come in the list. So 4 have the index 5, so that will append in this. So like this, next step 4, 5, and then 5, 4. Again sort, then this is the lowest index. So that will next 5 will be selected. This one. Okay. Now after selecting 5, you can see this is now. Okay. 7 is free without in degree. So 7 index is now 6. So that will include in this.
So that means that like in each iteration, for all the vertices which have in degree 0, you have to sort them based on preference.
Yes. So based on the index actually in the preference list, sort them and then identify that which node have the smallest index actually. Okay, so smallest index is representing a highest preference. So this is the additional part you need to do in the topological sort algorithm. Same topological sort algorithm you can use in this question statement. So this algorithm you can use. So first understand that how topological sort works. Okay, so the basic concept is simple. So if I just explain the concept, you can see the next slide. So this inside this. So you can see suppose we are starting from 1. So 1 have actually 0 in degree. You can see there's no edge coming on the 1. So we can start with this. Otherwise, all nodes have some in degree. In degree means how many edge are coming on that node, that number. So 1 we can start. After selecting 1, we will remove this. So you can see in degree of 2 and 7 will reduce by 1. So in degree is maintaining, we are inside this list. So you can now 2 become 0 and 3 become 0. And 4 also have the in degree 0. So now we have 3 nodes which have in degree 0. Okay. Now we will pick smallest one. So which is actually 2. So this is simple actually topological sort, but for the question statement, when we are getting in many nodes in with the in degree 0, we will identify the preference order, which one have the lowest index. So that things actually you need to do here only. Otherwise, the same step you will find.
Sort the tuple at each iteration.
So each iteration, just find out the smallest index with for the in degree nodes, 0 in degree nodes, and pick that node. Okay. So every time just pick that node, or 2 is now picked. So after picking 2, we have removed all the that adjacent edge of that and updated the in degree of the all adjacent nodes. So this is the repetition process. After every time we will select a node, we will repeat all the dependency for that node and then we will update the degree of the connected nodes. Then again we will repeat the same thing. We will again pick the degree 0 nodes, then we will repeat the same things. So this is actually a topological sort, and same problems we have this third problem, this one. So here you need to write a topological sort code, but only this with this update, preference selections. Then you will get a answer. Okay, so this is the additional task you have in this. So I hope topological sort just understand from the that algorithm and try to perform this task. Okay, finding a preference, finding a node from the preference list if you are getting a more than one node with degree 0 only. If you are not getting more than one, just pick it without checking. Okay, so I hope you can try this.
Yes, sir.
Yeah, so already 11 is there. Yeah.
Sir,
Yes.
so this before this we did a second question, right? So that was like slightly involved. So it is medium difficulty, sir, in OPP.
Yeah, this actually these problems are now higher difficult. So these live coding problems are actually higher difficulty level because initial terms actually we gave the difficult questions in the terms, but later we found that students are not able to solve that type of problems. Now the difficulty level is reduced in the OPP exam. Okay, so in coding live coding problems, we are actually solving the higher difficulty problem, higher level problem actually. OPP exam you will get a compared to the lower difficult level problems. Okay.
So if you are able to solve live coding, then OPP will be easy.
Definitely. Live coding, grading problems, practice problems, all are actually enough for the OPP exam. Okay. So yeah, generally we also shared that what are the area for the question actually. So definitely in OPP exam, one question will definitely come from the graph, either from WeeK-4 and WeeK-5. One question will definitely come. Okay, so some important algorithms are there. This BFS, topological sort. Okay, and these algorithms are important from WeeK-4. From WeeK-5, shortest path algorithm, spanning tree algorithm. So at least learn 4 5 algorithms for the these 2 weeks actually, WeeK-4 and WeeK-5. So you can directly solve one questions in the OPP exam. Okay. So,
Sir,
huh?
sir, for the live coding problem one, I'm getting
Mhm.
2 out of 3. But in one case, I'm getting error, but not in other.
What error you are getting?
Can you check that? I
Mhm. Check.
posted the code in chat.
This is complete code.
It's
Meaning
weak for
of
live coding problem one.
So let me copy this. Mhm. Okay, so E label parent you are calling the shortest path empty, parent is equal to -1, shortest path is equal to start. Okay, then P equal to E. Okay, shortest path equal to E. And then P equal to E and shortest while P is not equal to start. And P. So here start node is not added, I think. So what you're getting. This.
Yes, sir. Case 2 and 3 are passing.
Okay, so P equal to parent P, key error -1. Okay. So if you are getting this situation, so what you can do, you can stop the process at this step. So you can return directly a list like this. So shortest path equal to this and return. Okay, and shortest path. Because this is the one situation, you can directly stop here without checking the remaining part. You can see, because what you are doing, you are setting this equal to shortest path equal to start. Okay, if that E is not reachable, but still you are check after doing this step, still you are performing the remaining task here. Okay, you are setting this P equal to E, then you are appending the P in your list, and then also you are finding out the this P does not equal to start. So this is also becoming true because P is now a E, correct now. So this is also
Yes,
true.
P
And
minus
in this case, actually, parent of P is now become a -1. So this P is contain -1, and now you have appended this, and in the next step, you are doing the same thing. So P is a -1, which is also not equal to start, but at that next step, parent of -1, this become a error. Okay, so parent of -1, this value is coming actually. This node is not coming. So this is one case. If you are getting not reachability, return the answer, not store the answer, stop the process. Do not perform anything after that. Okay, so return means your code will stop here at this point. Or what you can do, you can use else condition. If you are not doing this, use the else condition like this. Okay, so just use else. If this is true, then this is fine. Otherwise, do this inside this case. Okay. So in this case, your only one part will be actually performed, either if or else. So okay, else. Okay. So yeah, this is the only error. Fine.
Yes, sir. No, it's working.
Okay. Okay, so try to solve third problem. Okay, now you got the logic and everything, so you can try, or you can also ask in the next session. Okay, so I hope we can close the session. Thanks everyone. Good night.
Thank you, sir. Good night, sir.
Thank you so much.
If you have to find the longest path, then you have to use DFS, right?
That is not guaranteed actually. Okay, so maybe it may be return longest path. That is also depends on the nodes, how that actually algorithm is implemented, which actually, so according to the DFS, so that actually traverse the one of the adjacent nodes and that enter into the next level. Okay, but what happens, suppose if entered first, that in the first node, okay, suppose that have the 4 adjacent nodes, and suppose longest path contain the another adjacent, but that enter into the another nodes. So in that case, maybe that will not return a longest path also. So that is not guaranteed actually. And longest path problem is also a that comes under the NP hard problem actually. Hard, that solution is not available because for the longest path you can repeat a like a cycle, then you can make more longest.
Yes, sir. But cycles are not allowed. Like in GRPA 3, asked to find the longest path. So
No, that is actually a the topological sort problem, not the DFS one.
it's a DAG.
DAG based problem. That is not the DFS problem.
Okay.
Okay. that is
Okay, sir.
given as a tag. Okay. And
Thank you, sir.
Thank you, sir.
okay, thanks.